very pleased with this opportunity to say a few words about reference governors and related algorithms for control of systems with constraints. Before I begin, I would like to acknowledge Professor Eleanor Gilbert at the University of Michigan, who has first introduced me to these ideas many years ago. Quite a few of my collaborators, I'm not going to mention them by name here, but they are co-authors on our joint publications, and many others, including organizers, of course, of ICINCO, for inviting me to give this talk. So my talk is about control schemes for systems that have state and control constraints. So the first question is, what are systems with constraints? Well, first, in traditional control design, the objective is to design a controller that generates a control signal U of t to track reference command denoted by R of t, that's a set point if you like, by a suitably chosen performance variable Z of t. So we'd like Z of t to be approximately equal to R of t, and this should happen despite disturbances, uncertainties, and here they are denoted by W of t that may act on a plant, and a plant is the system, of course, being controlled. Now, when a system has state and control constraints, what it means is that there are additional requirements that certain variables or outputs denoted by Y of t, outputs of the closed loop system, belong to a given set denoted by capital Y, and this should happen for all time instants greater or equal than 0. And so if you think about what constraints might correspond to, they may correspond to actuator range and rate limits, safety limits, comfort limits, as well as obstacle avoidance requirements. One of the prototypical examples of a constrained system, in fact, severely constrained system, is an aircraft gas turbine engine. Such an engine has great many constraints, including low pressure compressor surge margin, high pressure compressor surge margin, overspeed over temperature limits, combustion lean blowout limit, flight idle limit, actuator range and rate limits, and so on and so forth. The control system of the gas turbine engine actually consists of two separate parts. One of them is a power management, and the second part is limit protection. And it turns out that the limit protection subsystem that takes care of constraints in such an engine is in many ways more extensive in terms of algorithmic and software footprint than the power management subsystem, which adjusts fueling rate to generate desired thrust. These photos show negative consequences of aircraft gas turbine engine surge, that is, violation of compressor surge margin constraints. You can clearly see flames coming out of the engine, which is obviously undesirable and can